In the previous video, you learned about decimal or base 10 representation of an integer, which is how humans think about numbers, and binary or base 2 representation, which is how computers think about them. It turns out that binary isn't the only way computers represent numbers, though. There are two other number bases that are commonly used, and in this video, we're going to learn about those. We saw in the last video that the usual base 10 or decimal representation is where you think of a number as a sum of copies of powers of 10. We use 10 because most humans have 10 fingers, but what if you encountered an alien species with 8 fingers? They would probably count the same way, but their system would involve representing a number using copies of powers of 8 and only the digits 0 through 7. That's not actually science fiction, but a common way for computers to represent integers. So just as it's possible to write any number as a sum of copies of powers of 2 or 10, we can write any number, and remember this means non-negative integer for now, as a sum of copies of powers of 8. When we do this, we are using the base 8 or octal representation of that number. Here are the powers of 8 from 0 through 11 for reference. If some of these look familiar, remember that 8 is a power of 2, and so all of these are also powers of 2, which we saw last time. In the last video, we practiced with converting an integer from decimal to binary and vice versa. Let's do the same thing now with octal. Look at the integer 196. This is in decimal form. It can't be an octal because the digit 9 does not exist in octal. We can write 196 as 196 is 3 times 64 plus 0 times 8 plus 4 times 1. Remember, we're using powers of 8 here, and because of that, we can use the digits 0 through 7. We're not restricted to just 0 or 1. As with base 10 and base 2, writing 196 in base 8 means stripping off the digits in the second row and writing them as a string. So 196 in base 10 is 304 in base 8. Notice we say 304, not 304, because the 3 here is not hundreds. It refers to a power of 8, not a power of 10. Likewise, let's say we have 1402 that's represented in base 8. What is this number in base 10? Just like with binary, converting from octal to decimal is easy. Just count up the powers of 8. 1402 is 1 times 8 to the third, plus 4 times 8 to the second, plus 0 times 8 to the first, plus 2 times 8 to the 0, and that equals 770. Converting from binary to octal is easy too. In fact, octal is often used to shorten up binary strings. Given the binary string, group the bits into threes and convert each group of 3 bits to a number between 0 and 7, and that's your octal representation. For example, take the binary integer 10110001. Group into threes, 010, 110, 001. We added the 0 on the far left to pad this so we get even groups of 3. Now convert each group to decimal, which is easy because the numbers are small. 010 is 2, 110 is 6, and 001 is 1. The resulting octal integer is 261. As a decimal, this would be 177. Continuing this trend of using number bases that are powers of 2, another common base used in computer science is base 16, known as hexadecimal. If you've been around computers, you have probably seen hexadecimal numbers. They're sometimes used, for example, to represent colors in web design. For example, this website lets you dial up a color using hexadecimal code. They are also used sometimes in URL shortening services and in many other places. Hexadecimal, or base 16, is the same idea as base 2, 8, or 10, except instead of writing an integer as a sum of copies of powers of 2, or 8, or 10, we write it as a sum of copies of powers of 16. Now this introduces something curious. In base 2, we use digits either 0 or 1 to represent the place values, and in octal, we use 0 through 7. In base 16, we used 0 through 15, but that would get confusing to use two decimal digits to represent a single place value. So we use the ordinary 0 through 9 to represent 0 through 9, but for 10, 11, 12, 13, 14, and 15, we use the letters A, B, C, D, E, and F. For example, the hexadecimal number 1A8 is 1 times 16 to the second plus 10 times 16 to the first plus 8 times 16 to the 0, and that is 424 in base 10. Converting the other way, look at the decimal number 250. Written as a sum of powers of 16, this is 15 times 16 to the first plus 10 times 16 to the 0. The digit 15 is represented by the letter F, and 10 is represented by A. So 250 in base 10 is FA in base 16. Hexadecimal is widely used because it crunches the size of an integer down into a smaller string of digits. Notice that the 3-digit decimal integer 250 is only 2 digits long in base 16. In binary, the result is more dramatic. To convert from binary to hexadecimal, similarly to how we converted binary to base 8, group the bits into 4s and then convert each group into 0 through 9 or A through F. For example, 10110001 would be grouped as 1011 and then 0001, which would convert to 11 for the first group and 1 for the second group, which is B1 in hexadecimal. Hexadecimal, in other words, represents a binary integer in 1/4 of its original length, which saves on storage. Finally, here's a dad joke for you. Why did the computer scientist always get Christmas and Halloween mixed up? It's because oct 31 is des 25. Okay, so in this video we learned about octal or base 8 representation, hexadecimal or base 16 representation, and how to convert back and forth between base 2, 8, 10, and 16. Next up, we're going to address a missing piece, which is an algorithm to quickly convert from decimal to any of these other bases.